NASA's return to the moon was once framed as a single, clear path. SpaceX's Starship would handle the lunar landing. Artemis 3 would carry astronauts back to the surface, and the timeline seemed defined. But over the past year, that picture has become more complex. Development schedules have shifted. China's lunar program has accelerated, and NASA has quietly asked its industry partners to explore ways to move faster. In response, Blue Origin has put forward an alternative approach, one that could potentially place astronauts on the moon without relying on orbital refueling, one of the most technically demanding parts of the current plan. This proposal does not replace the existing architecture, but it does introduce a different way of thinking about how a lunar landing might happen sooner. So let's take a closer look. If you value clear, step-by-step breakdowns of complex space missions without hype or speculation, consider supporting the channel so more of these explanations can reach you as developments unfold. NASA is currently preparing for Artemis 3, the mission intended to return astronauts to the lunar surface for the first time in more than 5 decades. Under the existing plan, SpaceX's Starship serves as the human landing system, the spacecraft that would carry astronauts from lunar orbit down to the moon and back. However, Starship's development timeline has extended beyond earlier projections. At the same time, China has publicly outlined its goal of landing astronauts on the moon before 2030. In this context, NASA formally asked both SpaceX and Blue Origin to present options for accelerating their lunar landing capabilities. Blue Origin responded by advancing work on 2 versions of its Blue Moon lander. The first is Mark 1, an uncrewed cargo lander intended for early lunar missions. The second is Mark 2, a larger crew-capable lander designed for later Artemis missions. Because Mark 2 may not be ready in time to support Artemis 3, Blue Origin has outlined a potential intermediate configuration, sometimes described informally as Mark 1.5. This concept would adapt existing hardware to create a smaller crewed lander capable of reaching the moon without orbital refueling. To understand Blue Origin's proposal, we first need to clarify what makes the current lunar landing architecture so demanding. Under NASA's existing Artemis plan, astronauts would travel to lunar orbit aboard the Orion spacecraft. From there, they would transfer to a human landing system. In SpaceX's case, that system is Starship, a very large spacecraft designed to be refueled in Earth orbit before heading to the moon. Orbital refueling means transferring cryogenic propellant, extremely cold liquid fuel, from one spacecraft to another while both are moving at orbital velocity around Earth. This process has never been demonstrated at the required scale. It involves fluid transfer in microgravity, thermal management to prevent boil-off, and precise coordination between multiple launches. Technically feasible, but complex. Blue Origin's alternative avoids this step entirely. Instead of launching a single, very large lander that must be refueled in space, Blue Origin proposes multiple launches with more narrowly defined roles. The central idea is to use modified versions of its Mark 1 cargo lander as propulsion stages. What does that mean? A propulsion stage is essentially a spacecraft segment whose main function is to provide thrust. In this case, stripped-down Mark 1 vehicles would act as space-based boosters. After launch, they would rendezvous in Earth orbit with a smaller crewed lander, the proposed Mark 1.5. These booster stages would then fire their engines to push the crewed vehicle onto a trajectory toward the moon. This still requires several launches, but it removes the need to transfer fuel between tanks in orbit. Each vehicle carries its own propellant from launch. Now the critical question becomes, can the mass budget support this? Mass margin, the difference between the maximum weight a launch vehicle can carry and the actual spacecraft mass, is one of the most restrictive constraints in spaceflight. Launch vehicles in the roughly 45-ton class would need to lift the crewed lander along with life support systems, structural reinforcement, radiation shielding, avionics, and fuel. Life support includes oxygen generation, carbon dioxide removal, temperature regulation, and water recycling. Radiation shielding protects astronauts from solar and cosmic radiation, which is more intense outside Earth's magnetic field. Each of these systems adds weight, E. Once those components are included, the remaining propellant available for the lunar transfer maneuver becomes limited. The target orbit for Artemis missions is called Near Rectilinear Halo Orbit, or NRHO. This is a highly elliptical orbit around the Moon that provides stable communication with Earth and efficient access to the lunar South Pole. Reaching NRHO requires precise energy management. If propellant margins are tight, the spacecraft must operate with very little performance buffer. That increases engineering sensitivity to small deviations. Blue Origin's approach gains credibility because Mark 1 and Mark II already share major components. Both use the BE-7 engine, a liquid hydrogen and liquid oxygen engine designed for deep space operation. They also share similar tank structures and avionics systems, meaning guidance, navigation, and control hardware are largely compatible. However, adapting a cargo lander into a crew-capable vehicle is not a simple swap. The crew cabin sits within the structural load path, the primary pathway through which mechanical forces travel during launch and landing. Changing cabin size alters how stress is distributed across the vehicle. That requires structural redesign and requalification testing. Additionally, the transfer stage must remain compact enough to fit inside the protective fairing, the nose cone of the launch vehicle, while still providing enough thrust and propellant to perform the Earth-to-Moon injection burn. Every design adjustment affects another subsystem. In short, the architecture simplifies one major challenge, orbital refueling, but shifts complexity into mass optimization and structural integration. At first glance, this may appear to be a technical variation between companies, but the implications extend beyond engineering preferences. Artemis 3 is not simply another lunar mission. It represents the first time in more than 50 years that astronauts would attempt to land on the Moon. Unlike Apollo, the Artemis architecture involves multiple new systems operating together for the first time. A new deep space crew vehicle, a new lunar landing system, new spacesuits, and a new mission profile built around NRHO. When several first-of-their-kind systems are stacked into a single mission, risk compounds. Even if each system performs well independently, integration introduces additional uncertainty. If Blue Origin's alternative approach were technically viable, it would offer NASA another pathway to reduce dependency on a single landing architecture. In strategic terms, redundancy increases program resilience. If one system experiences delays, another may preserve schedule momentum. There is also a geopolitical dimension. China has publicly targeted a crewed lunar landing before 2030. If the United States aims to maintain leadership in human lunar exploration, schedule credibility becomes significant. If Blue Origin can demonstrate uncrewed lunar landings with Mark 1, validate propulsion reliability, and prove structural performance under lunar conditions, NASA would gain real flight data before committing astronauts. That step-by-step validation pathway could lower cumulative mission risk. Additionally, avoiding orbital refueling, if proven workable, would remove one of the least demonstrated elements of the current plan. Refueling in orbit is possible in principle, but it requires multiple perfectly timed launches and propellant transfers at scale. Eliminating that variable simplifies mission choreography. None of this guarantees acceleration. Engineering constraints remain substantial, but if the architecture performs as intended, it could offer NASA flexibility at a critical moment in the Artemis timeline. Despite the structured proposal, several variables remain unresolved. First, performance margins have not been publicly detailed. Whether the hybrid lander can carry sufficient propellant, life support systems, and structural reinforcement while remaining within launch constraints will depend on detailed mass accounting. Small deviations in weight can significantly affect mission feasibility. Second, the timeline depends on successful uncrewed demonstrations. Blue Origin plans to test its Mark I cargo lander in lunar conditions, including operations near the Moon's south pole. These missions must validate propulsion restarts, thermal management through extreme temperature swings, autonomous landing precision, and system durability. If those milestones slip, the crewed pathway would likely shift accordingly. Third, integration with NASA's broader Artemis framework must align. The lander must dock with Orion in lunar orbit, interface with mission control systems, and support astronaut surface operations. Each integration point requires testing and certification. Looking ahead, key milestones to monitor include the first Mark I lunar landing attempt, structural testing of the hybrid configuration, and progress on Blue Origin's New Glenn heavy lift rocket, which would support launch operations. If those demonstrations proceed successfully, the proposal could move from conceptual alternative to operational candidate. If delays emerge, NASA's existing architecture remains the baseline. For now, the situation reflects an evolving landscape rather than a final decision. The path back to the Moon is still being shaped by engineering results, schedules, and geopolitical timing. As those elements develop, the architecture may continue to adapt. We will continue following these milestones closely as new data becomes available and the next phases of Artemis take form.